Okay, let's get started. Okay, so a new homework's coming out today, and I think you'll like it. I think it's going to be fun. It's a lot of computational stuff with Poisson processes. And the exam, I'm still aiming for, really hoping and trying to get them back on Friday. And I think that's going to happen. So, but they're going well. You guys are doing great. Um, Yeah, and grad students working on the take-home, there is a link to upload it, and you'll find that in Canvas under the assignment, so it's not in grade scope. Okay, any questions on anything before we get started? I'm going to work on sharing my screen. So I was asked for a hint on problem 2 on the grad take-home exam, and in this problem, you have this function, this m. So this is number 2 on the take-home exam. You have this mij, which is the expected number of hits on state j between 2 visits to state I. Okay, so to get started on this, I would let ti be the first return time to I, the first return time to I, and if you want to write that more formally, it would be the minimum over all times greater than or equal to 1, such that xn is equal to I. And so then we can have, or we can write, so now we have mij as the expected values. So this is going to be the expected number of visits. So I started with an I, so there's an I down there, which is really hard to read. It's getting a little sloppy. And then I would sum up a bunch of indicators, but you don't sum them up forever. You sum them up only until the first time you return to I. So something like the sum as n goes from 1, we're only counting the hits after time 1. And if you, so the problem already told you that m sub I of I is determined already. Or is it? Well, you might have to do that as a special case. But right now I'm assuming that j is not equal to I. So I'm going to sum up to that first hitting time or first return time to I, an indicator if the chain is in state j at time n. I'm going to sum over all those n's. So that is the expected number of hits on state j between 2 successive visits to state I. Okay, so just a little more. I don't want to take away all the fun, but I think you're going to want to pull the sum out of the expectation and talk about the expectation of an indicator, which is a probability. However, you can't pull it out as written because of this random variable up here. But you can if you rewrite it like this. So the expected value starting from I, the sum as n goes from 1 all the way to infinity, the indicator that xn is equal to j, and so I can indicate 2 things down here, or equivalently, I can look at a product of 2 indicators, but I want my n's to be less than or equal to ti. So now you can pull this sum out. The expected value of the indicator is the probability of the event being indicated. And if you look at where you're trying to go, I think there was like a pkj in there. I would look at that probability and I would condition on where we are at time n minus 1. Like maybe we're at k, and that's how you move from k to j in one step, coming from maybe a conditioning on where you are at time n minus 1 being k and running over all k. Okay, so let's talk about Poisson processes. I already had some stuff written, so let me back up here. Just as a review, a Poisson random variable has this PDF, and its mean and variance are both lambda, and lambda is a parameter for this distribution, which has to be greater than 0. So that's the Poisson distribution or random variable, and we use that to define a Poisson process. Now, before defining a Poisson process, we define something a little more general, and that is a counting process. So we are using this kind of notation where we went from kind of discrete time to continuous time. And absolutely, people can write it like this still, but I like to keep them separate in a classroom environment, like subscript and then of t. And the counting process is so special that we're not going to use up the name X on it. It's going to get its own N. So N of T is going to count the number of events that happen up to and including time T. And for us, the event is usually going to be the arrival of someone or something, like a query to a process. It's the arrival of something. So we call these inter-arrival times or inter-event times. Oh, I'm not breathing. But these X's that I drew down here, these are at some random times. They're of differing lengths. And at each time point, this process jumps up by 1. So that's a counting process. And then we had the definition of a Poisson process. And I called this definition 1 because I have 3 definitions, and I think they're all going to be useful. I think you're going to care about all of them. But definition 1 starts with a counting process, and it has these 3 properties. So property 1 is we always start with a count of 0, and this could be changed, but it's a convention that makes a lot of things easier. Condition 2 is called the independent increments condition. And so let me back up a little bit. The value of the counting process that I've drawn here, certainly the value of the process at, say, this time is not independent of the value of the process, back here. It's actually exactly 1 more, and it depends on the length of time that happened back here. But the increments are the jumps you're making. So if you look at any 2 points, like say here and here, and maybe here and here, if you look at the number of jumps in there, which is given by the number that this process takes on at the right endpoint minus the number at the left endpoint, that gives you the number of jumps you're seeing in that interval. And those are independent. So N of T1 is not independent of N of T2, but these kinds of differences are. And we call that the independent increments property. And the third and final property for our first definition involves the Poisson distribution. And it is that if you take an S greater than or equal to 0 and a T greater than 0, if you look at, I'm going to keep saying arrivals. Poisson process is usually the arrival of something or the occurrence of an event. So this is the number of arrivals in the interval from S open to S plus T closed. Not that you can get an arrival exactly on that right endpoint, but technically it does include that. And so the assumption 3 to make a Poisson process is that the number of arrivals in there has a Poisson distribution, and its parameter is the rate parameter for the process times the amount of time you're looking at. So this is an interval of length t. And because this distribution, this Poisson distribution, does not depend on S, no matter where you put that interval of length t, you'll have the same distribution of the number of jumps. So we have this distribution that's not changing in time, that is being stationary. And that's why we call this the stationary increments property, although saying stationary increments alone is not enough to tell you that it's specifically a Poisson distribution. Whereas saying independent increments back here is kind of enough to not have to write all the other stuff. So that's old stuff, but is there anything I can clear up before we go forward? I got a great question last time, and that is about this process appears to have a kind of lack of memory. And what does it have to do with the exponential? And in fact, our definition 2 will be defining the Poisson process in terms of an exponential distribution. So there's a very close relationship. But before then, I want to just work out a couple of kinds of simple computational problems. So I just want to emphasize that the game is always to take advantage of the independent increments property. Right before this, I just want to put some notation down. So we will be using T1, T2, T3, Now, I know these look like other things we've used, but I don't think there will be any confusion in the context. I mean, T is a pretty common letter, but these are going to be to denote the inter-arrival times. Inter-arrival or inter-event times. So our Poisson process is a kind of counting process with extra properties. So it is going to look like a step function. And so it'll be 0, and then it will jump up by 1, and then it will jump up by 1 and jump up. That doesn't look like 1. Jump up by 1. And so the times, so what I'm trying to say that is this is T1 and this is T2. So I'm not saying like this is time T2. That is in fact T1 plus T2. And to continue in this picture, this little interval here is T3. And this, I don't know, actually, I can't see the rest of that drawing. So the T's are going to be inter-arrival or inter-event times. And then one more point of notation, I'm going to use S's, so S1 through Sn. Sometimes I've used these in the other order, like I've used S's where I use T's, but I've decided to fix them this way because S's look like sums, and that's what we're going to be using them for. So I'm going to let Sn denote the time of the nth arrival, which is going to be made up of the sum of the T's all the way up to time n. Now, I'm not saying anything yet about the exponential distribution, but you can see why we talked about some of those sums last time in moment generating functions, because if these T's are IID exponential, then the time you have to wait until the nth arrival happens has a gamma distribution with parameters n and lambda. And I will write that down eventually. I'm just saying it conversationally right now because we kind of talked about sums last time. Yeah, you could. It's just, I don't know. Usually this is thought of as the, let me get it. This is, so here is where the first arrival happens. And this is thought of as the time it takes until the first arrival happens. I mean, you could, but usually people don't. So with that notation, I wanted to do some quick and easy examples of kinds of computations that you would have to do with Poisson processes. And the thing that I want to emphasize is that you really want to take advantage of the independent increments kind of property. Not kind of, it's a property. So you really want to take advantage of independent increments of a Poisson process. So suppose, let's look at an example, just a nice concrete example. Let's suppose we're looking at a Poisson process with rate 2. Suppose that the collection of random variables indexed by continuous time t is a Poisson process with rate 2. So that means the lambda is 2. So I'm going to have a bunch of questions here, an A, B, C, D, maybe even through an F, but they're going to be pretty quick. The lambda is 2. Okay, so for part A, let's find the probability that the number of arrivals by time 4 is 3. So I absolutely don't expect you to write this next line. I'm going to write it for our first time seeing this. This is the number of arrivals at time 4 minus the number of arrivals at time 0, which is 0. And now it's really easy to match up with our definition of the Poisson process. This is a Poisson random variable, not a process, just a random variable with parameter equal to lambda times the length of the time interval, which is t here. So we're just going to use the Poisson PDF with a lambda t in place of lambda and plug in 3's. And we get e to the minus lambda t to the third. Oops, sorry, my t is fixed here, it's 4. I forgot that I had an actual t. So t equals 4. Back up and try that again. So this is going to be e to the minus 4 lambda. 4 lambda to the third over 3 factorial. We didn't use independent increments there, but we will in, hopefully, yeah, we will in part B. Okay, my next question is, what is the probability? So this is going to be a joint probability that n of 4 is equal to 3 and n of 7 is equal to 5. So we have 2 random variables here, and they are dependent on each other because they are accumulating these steps up in the counting process. So for example, if this were the other way around, the probability that n of 4 is 5 and n of 7 is 3, that probability would be 0 because this is saying you have 5 jumps by time 4, but you only have 3 jumps by time 7. You know, that can't happen. So they're pretty dependent. So I want to take advantage of the independent increments property and rewrite this as the probability that at time 4, I've had 3 arrivals or jumps. And then between time 7 and time 4, the increments of the amount of jumps is 2. I got 2 more to get up to a total of 5 jumps. And you can think about the events in both of those probability statements, go back and forth. It is an if and only if situation. And now this random variable is independent of this one. And again, I'm using the fact that n of 4 is n of 4 minus n of 0. So it is, in fact, an increment. So I get to break this up into a product by independence. Independence. And then these are Poisson things. So this guy is a Poisson random variable with parameter 4 lambda. You know what? I had a lambda too. My lambda was 2. I think I'm going to purposely leave that out because if I use total numbers everywhere, then that will be an 8 and it will be hard to see what came from where. So yeah, throughout these, lambda is 2, but I'm not actually going to plug that in. So you can see the different pieces. But that's a Poisson with parameter 4 lambda. And this is not that with the probability, but the random variable in there is Poisson with parameter 3 lambda, because 3 is the length of the time interval between time 4 and 7. So we want to use the Poisson distribution with those rate parameters and plug in 3 and plug in 2, and we get e to the minus 4 lambda to the third over 3 factorial times e to the minus 3 lambda to the second over 2 factorial. To C. And my C is a conditional probability. What is the probability that the number of arrivals at time 7 is 5, given that the number of arrivals by time 4 is 3? So first I'm going to do this a little bit informally, which I think is fine because it does kind of demonstrate your understanding of the Poisson process. But I imagine that some people would like to see it a little more formally. So I've had 3 arrivals by time 4, and I want the probability of 2 more arrivals in the next 3 units of time. So I claim that this is just the probability that n of 7 minus n of 4 is 2, right? So the picture, I have 1, 2, 3 arrivals at some time 4, and then I want to look later at time 7 and see that I've had 2 more jumps. So I want to count the total number of jumps at time 7 and subtract the total number at time 4, and I want to see 2 in there. And if you wanted to leave the conditional part, that's okay. But now in the next step, you would delete that because this increment, this random variable, is actually independent of n of 4. So again, this is the informal approach. I'll do it more formally in a moment. But this is the same thing as, now you don't have to write this part. You can just go straight to the answer. But by stationarity, this is the same thing as the probability that n of 3 is equal to 2. In the picture, n of 7 minus n of 4 is different than n of 3, right? N of 3 is how many jumps I've seen by time 3, and n of 7 minus n of 4 is how many jumps I see between times 4 and 7. But they'll have the same distribution as the number of jumps I see in any other interval of time with length 3. So you don't have to write this line, but either case, we have an e to the minus 3 lambda because we have a time interval of length 3, then 3 lambda to the 2 over 2 factorial. So sometimes you'll see me doing these changes, and if I forget to tell you why, hopefully I won't. I'm not saying that n of 7 minus n of 4, this is not equal to n of 3, but they're kind of equal in distribution, which you might write as an equal sign with like a letter D over it. They will have the same distribution. So more formally on this one, I'm going to continue this example and then I'll ask if there were any questions. So more formally, so the conditional probability that n of 7 is 5, given that n of 4 equals 3. That's what we just found, and we did it kind of using independent increments and kind of more intuition. If you really wanted to find this more formally, this conditional probability would be the joint probability of both of them divided by the marginal probability of the given one. And then, like we did part B, I would use independent increments to break up the top into the number of arrivals by time 7 minus the number of arrivals by time 4 is 2. The number of arrivals by time 4 is 3 over the probability. The number of arrivals by time 4 is 3. And then I would use independent increments to break up the top. So I get blah, 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 blah. So I get this thing on the end, which is going to cancel with the denominator. And this brings me back down to kind of where we started before, with a little more of our intuition maybe than mathematics. So it's the same problem. And I'm okay if you go straight to this in your homework. I just wanted you to see maybe a slightly more formal approach. But wait, there's more. Talk about D. So what I was saying was in that problem, it's just like what I do. The probability, it could have been a different problem. So it was N4 is 3 and N7 is 5. So the probability that N4 is 7 and N3 is 5, I said that that was 0 because, so here's time, and here's some time 3 and some time 4. And so this is telling us that we've had exactly 3 arrivals by time, I'm sorry, exactly 5 arrivals by time 3. There's one arrival, 2 arrivals, 3 arrivals, 4 arrivals, 5 arrivals. And so now this other part is saying, oh, but you have a total of 7 by the time you reach 4. And no. Turn these around. Because if I had 7 by time 3, I can't have less by time 4. And that's why that probability is 0. Let's do another one. Another simple computation. And let's kick it up a notch and bring in our inter-arrival or inter-event times. So suppose you want the probability that n at time let's make this kind of generic. Time t is 3 given t1 is greater than t. This is what we just talked about, really, because t1 is the first inter-arrival time, and that's actually the first arrival time. Like, we'll go t1 units of time before we see our first arrival. So we're at 0 here, and then we jump up to 1 here. And so if the first arrival is happening at a time greater than t, then we have seen 0 arrivals at time t. So this probability is 0. And let me write that. So this is since no arrivals by time t, since t is earlier than the first arrival. If you'd prefer to use, well, I haven't shown you yet that the Poisson process is Markov. Hopefully it is, or this was all a waste of time. But if you want to try to use the Markov properties, you can rephrase a lot of these things that appear to have kind of mixed, like we're talking about the Poisson process, and over here we're talking about inter-arrival times. You can often rephrase these kinds of things in terms of the process. So like the event that T1 is greater than T is equivalent to the event that the number of arrivals at time T is 0. So here's time T. If the first arrival isn't until after T, then there were no arrivals in here. And if there were no arrivals in here, the first arrival isn't until a time after T. So it wouldn't have been wrong to start this guy up here and rewrite it as the probability that n of t is 3 given n of t is 0. That actually makes it much more clear that this is the probability is 0. And then we're going to prove that this is actually a Markov process. So for my, where are we? D. Actually, I want to do 2 more. So for my ETH trick, I'm going to take 2 time points, s less than t, and both of these I'm going to make greater than 0. If I want the probability that n at time t is 3, given t1 is s, so this is no longer a trivial thing where clearly this can't happen, because the picture is there's some time s and there's a later time t, and I know that the first arrival happens precisely here. Now, the probability that the first arrival is precisely there is 0, because this is a continuous variable, but it can be on the right of the conditional line because that's something given, already measured, already fixed. So the probability that the next person you measure has a height of exactly 67.72 inches is 0. But once you measure them, assuming you're measuring with infinite accuracy, you can say you have that person. Right. So we can do this more formally, but I'm going to do this less formally and say that this is the same thing as saying that the number of arrivals at time t minus the number of arrivals at time s is equal to 2. Because we know the very first arrival happened at time s. And so if we want 3 by time t, we need exactly 2 arrivals in between. So this is a Poisson random variable with a lot of s's with parameter lambda times t minus s. Yeah, lambda is 2, but I've decided to just stick with the lambda. And so this is e to the minus lambda t minus s lambda t minus s to the 2 over 2 factorial. And again, just like in the one before, I could rewrite this whole thing in terms of what's going on with the ends. If you really just want to use the ends because you're comfortable with those, because it's a well-defined process, And so let me just try the rewrite here. The probability that n of t is 3, given t1 is s. Suppose I want to rewrite this in terms of just the n process. So this is the probability that n of t is 3, given, okay, so we have n of s is 1, and n of u is 0 for all u less than s. So if the time of the first arrival is s, then at the time of the first arrival, the number of arrivals is 1. But also, in order for us to know that that was the first arrival, we need to say there were no arrivals before that. So again, if you would like everything in terms of the n's, and then you can use the Markovianness that we're about to prove for the Poisson process, then you can rewrite things always, almost always, in terms of the n of t process. Okay, so I do have an f. So f, let's talk about the probability that n at time 5 is, well, let's use 8 because otherwise, yeah, I'm going to use 8. Given that S2 is 2.3. So S2 is the time of the second arrival. T2 would be the amount of time that goes by to get the second arrival after the first arrival has come. But this is actually the time of the second arrival. So we've had an arrival, and the second arrival happens at time 2.3. So we want to look later at time 5 and figure out whether, or figure out the probability of having a total of 8 arrivals. And that just means that we need 6 arrivals in here. So this is the probability that the number of arrivals at time 5 minus the number of arrivals at time 2.3 is 6. And you could use stationarity to write this as, let's see, what's that a difference of 2.7? So you could call this n of 2.7. And again, n of 5 minus n of 2.3 is not equal to n of 2.7, but they are the same in distribution. They act the same as random variables. So I could rewrite this in terms of n of 2.7, but I won't. I'll just say this is an interval of length 2.7. So this is a Poisson number with parameters 2.7 times lambda. And I want to plug 6 into that Poisson PMF. So I get e to the minus 2.7 lambda, 2.7 lambda to the 6th over 6 factorial. All right. So as I said a couple of times, this would be silly for us to spend so much time talking about a Poisson process if it's not a Markov process. So right now I want to show that a Poisson process is a Markov chain or process. And at this point, I would usually pull out the definition of the continuous time process and remind you of that. I'm not going to do it. You'll see it as we go. So I'm going to take any integer n greater than or equal to 1 and any time points. I call them, when I defined a Markov process, S1 through Sn, and then an S and a T for the last 2 values. So S1 is going to be greater than or equal to 0, less than S2, less than up to less than Sn, less than S, less than T. And we want to look at the probability. This is the definition of the continuous time process. We want to look at the probability that n of t is j, given that n of s is some I, and the others are equal to some other values that I'm going to call in through I0. So n at time Sn is an In, down to n at time S0 is an I0. I'm a little rushed, so I'm not going to write this down, but we need to show that this is equal to this probability wherever these conditional probabilities are defined. So if I picked these I1s through INs incorrectly, so this didn't make sense. Like if I said that I had at time 1, I had 3 arrivals, and then at time 4, I had only 1 arrival. Like that happens with probability 0. That's not happening. And in the conditional probability, that's going to make the denominator have probability 0, and everything is undefined. But we need to show that this long conditional probability is equal to this shorter one whenever the conditional probability is defined. So I'm assuming that basically that my I0s are properly ordered. They can be the same. Little I0 could be little I1, but they have to make sense. Okay, you know how to do this. It's just how you do any of these problems. I'm going to use the definition of conditional probability and use the big fat intersection on top and a less portly intersection on the bottom. It's a good time for cut and paste, huh? Copy. I always say cut, and I'm meaning copy. Yeah, not when you get this extra stuff. Okay, so all I did there was this conditional probability. And now, just like we did our examples all the way through the last long example, we want to write this in terms of increments. So this is it's going to be a little weird starting from the left. I'm going to start from the right here. We're going to have n of S0 is I0. And then the next one is going to be n of S1 minus n of S0. This is poor planning all around. Is going to equal the I1 minus I0. All the way out to the beginning. That doesn't even make sense. N of t minus n of s is j minus I. So I'm really sorry about the scroll, but I just want to do this really quick. Go to B. We're just redoing B back in this example. We want a joint probability for the process being at certain values at different time points. So we rewrite it so that we're talking about the independent increments. Scrolling back. I'm going to do the same thing on the bottom. So I'm going to write this as, it starts with n of s sub n equals I sub n, but I'm going to turn it into the increment that n of s sub n minus n of s sub n minus 1 is in minus in minus 1 down to n of s sub 1 minus n of s sub 0 is I1 minus I0, and the last one, n S0 is I0. And now you get to use the independent increments. Again, I'm going to, I forgot what I was going to do. That was again, but let me just finish this problem. We break it up into the individual probabilities. I had a professor once take 2 points off of an exam I took because I was writing a dot, 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 and I only wrote 2 dots. He said that, I mean, that bothers me too, but now I'm in charge. So 2 dots it will be. Right. So if you collected all these terms, it's getting kind of messy. These are all the same up until the very first one here remains. And so you end up with the probability n of t minus n of s is j minus I. Now we're not done showing it's Markov, but I am out of time. But the thing you would have to do is say, on the other hand, start with the probability that n of t is j given n of s equals I, and rewrite it so that you get the same probability. Or if you want, you can kind of reverse engineer it and start from here and back up. But yay, it's Poisson, which means we get to talk about it more. And we will a lot more. Next time, definition 2, where we reveal those exponentials, and maybe even definition 3, which appears to have no structure whatsoever, which is why I think I can convince you that Poisson processes are useful, because there's not a lot of assumptions behind them, really. Now I'm out of time. We are done.